Okay, so if you remember from yesterday, we've been creating DFT runs, and so we needed to have the geometry file. And so we're going to focus a little bit more on this in this session. And I briefly highlighted how you could actually create structures automatically with the AFLOW software instead of having to put it in by hand and put each atom position and the different lattice vectors. And so how do we do this? So you may be familiar with some of the catalogs within the community, such as the Pearson's Handbook, the Strukturbericht series, forgive my German pronunciation, also the American Mineralogist Crystal Structure Database. And so there's many different resources available. However, it becomes a challenge when we actually want to use these in a computational framework. And one of the main hurdles is this idea of arbitrary designations. So for example, you may be familiar with the rock salt structure, and it can be referred to in many different ways. So for example, you may consider it as NaCl, so sodium chloride, magnesium oxide, or you may know that it has the Strukturbericht designation B1. And so there's many different designations for just this single structure, and it doesn't even actually tell you what the structure looks like. And so this can be a challenge, especially if you're not familiar with crystallography. Additionally, many of these resources will give the notation or the actual crystal structure with just the following information here. So for example, they'll give you space group 216 and maybe the Wyckoff positions for the silver atom, and they'll tell you the Wyckoff multiplicity, the letter designation, and the representative coordinate. But then you would need to go to an external reference, the ITC, the International Tables for Crystallography, and you would need to know that you need to expand out this coordinate by the symmetries to get the corresponding actual 4 atoms that it represents. And so again, if you're not familiar with this resource, then this could be a computational hurdle when you're actually trying to write out all of these geometry files. And so there's no way to actually generate these materials in an automatic fashion. And so this is a hurdle that we wanted to overcome. And so AFLOW has built-in structural prototypes within our software. So for example, we did see a few yesterday when we were actually creating some of the AFLOW-in files. So we saw that we had the Heusler structure. We also have the anti-Heusler, half-Heusler. And the idea here is that we have these backbone structures, so they don't have any elements on them yet. And then we go to the periodic table and we put different species on these different sites, or these different elements. And then we can create new hypothetical materials. And so this is the idea behind prototype decoration. And currently we have 600 online that we can view, and we'll view that a little bit later. And then we also have many, many more integrated into the software itself. And so this endeavor is known as the AFLOW Prototype Encyclopedia. And so this has been a synergistic effort with Professor Michael Mell, who originally started a prototype encyclopedia when he was at NRL. And so we've joined with him and we've extended this effort. And so we have an encyclopedia that has many different prototype structures, and we have many different characteristics and designations, such as the historical Strukturbericht, the Wyckoff positions, Pearson symbol, and many different attributes. And since this effort was joined with AFLOW, all of these prototypes are integrated into the AFLOW software. And so we can perform automatic materials generation with these structures. And so part 1 contained 288 prototypes. And this is similar to what was on the NRL website, but now there's 302 that we've extended to our framework. And so there's a total of 590 prototypes, and there's at least one representative from each of the 230 space groups. And we're already working on part 3, and hopefully that'll be coming out fairly soon. And so I also mentioned this idea of arbitrary designations. And so we wanted to come up with a descriptive label that we could use to generate these materials in an intuitive manner. And so we've come up with the AFLOW label. And so we did see a variant of this before in session 2. And so here is an example AFLOW label. And if you're you might actually recognize some of these symbols from the symmetry exercises that we did yesterday. And so here it's a string that's separated by underscores. And in this first field, we have the reduced stoichiometry of this structure. The second field is the Pearson symbol. The third field is the space group number. And the subsequent fields are the Wyckoff letters associated with the particular species for A, or in this case, the species B, the Wyckoff letters. And so in addition to this, we may need to provide additional parameters. And so these are the degrees of freedom consistent with the symmetry designated by this label. And so for example, here, for this particular label, we need to specify the lattice parameter A. We give the ratio C over A, and then we give the Wyckoff Z coordinates here. And so these are the only degrees of freedom that you can change that are consistent with this symmetry. And so this is actually very powerful because we can actually change these numbers and we can see how the structure changes. So in this case, we compressed the C over A ratio. And in this case, we shifted some of the Wyckoff positions. And so, but again, even though we've made these shifts, it still has this same underlying symmetry. And so this is a very powerful prototype tool because we can generate many structures just with this one label by changing the degrees of freedom. And so all of these prototype encyclopedia prototypes are online. So actually, let's go ahead and navigate there now, and feel free to follow along. So let's go ahead and open a browser. And we're going to go to aflow.org. And it should take you to the main AFLOW page. And if you scroll down, you should see the apps and docs section. And so here we're interested in the Crystal Prototype section. And so here is the main page for the Prototype Encyclopedia. So you can see we currently have 590 that are online. And so you can search the different prototypes by the, in the banner here. So you can search by space group, for instance. And so if you can click on maybe the monoclinic space group category, and they're organized by space group number. You can also search by Pearson symbol. So again, you go to the different classes, and then let's hit orthorhombic structures. And you can see they're organized by Pearson symbol here. There's also structubric designations. So if you're familiar with these, you can search by this. So for example, the B1 structure we saw was rock salt, cesium chloride, and etc. You can also search by chemical symbols, so alphabetic order by species. And so let's actually go to a particular page. So if you click on the encyclopedia icon, you're taken back to the main page. And let's go ahead and search for a particular structure. So if we go into the search field, let's look for corundum. You type that in, hit enter. And if you scroll down, you should see corundum appear. So one thing I want to mention about this search page is you can also perform more complex queries. So for example, if you wanted all of the structures that have space group 225 and that have a certain Pearson symbol, you can perform these more complex queries. But for now, let's just go ahead and click on corundum. So if you click on this, it should take you to the main entry page for corundum. And so it might take a second for JMOL to load. But so here is the corundum structure. And so we have a JMOL viewer, so you can rotate the structure. You can view it along different directions. You can load a supercell of this structure or a block. You can view the primitive cell of this structure or the conventional cell, or you can view both at the same time superimposed on one another. Hopefully everyone can see my screen. If not, please feel free to let us know in the chat. You can also visualize the Wigner site cell centered on certain atoms if you'd like. You can view, let's go back to the conventional cell. You can view along different axes, and there's different ways that you can play with some of the formatting options here. So if you scroll down, you'll see the generic prototype information. So this is AL203, so this is the common material that exhibits this structure. We also have the AFLOW prototype label, which I've highlighted already. Struct2brick designation, Pearson symbol, some more space group information. And then this is the actual AFLOW command that you would run to generate this. And so we'll see this a bit later in some of the exercises. We also provide a list, if applicable or if available, some other compounds that exhibit this structure, and maybe some useful comments for this structure if we found something interesting in the literature. We provide the primitive vectors for this particular structure, and you'll notice that it is in symbolic notation. And so again, this is useful because we can play with these degrees of freedom for the structure to create slightly different variants of the prototype. And then we provide the basis vectors. So these are the atoms in the primitive cell. And again, you'll notice that they're given with respect to X, Y, and Z coordinates. So again, these are tunable. At the bottom, we provide the original reference where we found the structure. There's some pre-loaded geometry files, so CIF and PostCar. And then probably the most important aspect is at the bottom of the page, and this is the prototype generator. And so you can see this is an example AFLOW command, so it may look pretty similar if you remember from yesterday. And here you can input the different degrees of freedom, and then you can also decorate with different species. And then you can create the geometry file by hitting any of these buttons. And we support a variety of different formats. So from yesterday, we should be familiar with VASP output. So if we click on that, you should see that this looks like the normal postcard. We also support different ab initio formats, such as Quantum Espresso. So you should be able to see the Quantum Espresso output, FHI aims, ab init, YCAR. So we saw this earlier in the symmetry session. So this is the symmetry version of the postcard. We also have CIFs. And then finally, you can refresh the JMO. So for example, let's say we wanted to do, I don't know, silver and iron, let's say, just as an example. And we wanted to see what the structure looked like. Now you'll notice that we've decorated it with different species. And again, you can also play with the degrees of freedom as well. And so this is an example of the prototype entry page. And so for each prototype, we have one page for it. And so before we leave this page, I want to point out two other things. One is the prototype index. So if you go to the top banner and click prototype index, you can see a list of all of the prototypes in table form. And we also have, again, some preliminary search functionality. So for example, if you wanted to see if we have multiple perovskites. So if you type perovskite, hit enter, and we actually have 3 of them. And so they have slightly different symmetries. And you can also sort the table by hitting the column. So you can sort by Pearson symbol, space group. And then if you want to get back to the main table, you hit reset. And again, the whole table is sortable. So if you want to sort by space group number, you can do that as well. And then if you'd like to learn more about crystallography, or if you'd like to know what crystallographic conventions we use in the encyclopedia, you can click on Crystal Info, and you should see the different crystal classes. And so if you click on triclinic, you can see how we define the lattice vectors and what space groups are in this particular lattice type. And we could go to, let's say, orthorhombic. And so you will see that we have the simple orthorhombic, the definition for the lattice vectors, the volume of the cell, and then also the space groups associated with this particular lattice centering. And also it, again, highlights this idea of what's the relationship between the primitive cell, highlighted by this gray box, and this hollow box, which is the conventional cell. And so if you look at this picture, you can see that the relationship between the primitive and conventional cell volumes is half, or 2. And then the last thing is at the bottom, you can look at the space group page. And so this tells you some information about the different space group notations used throughout the encyclopedia. And so you can see that we have the Hermann-Magouin, Hall, the international symbol, and the show and fleas. And so you can scroll through that as well. Okay, and then also a quick search if you want. So you can also type a search in here. So if you want rock salt, and then actually it might be case sensitive, or actually I think we did rock salt. There we go. Yep. So it looks like, so there was a question, I think, how do you get to the Crystal part of the website? So again, I'll just briefly go through it. So if you go to aflow.org, and so you should get to this page, and then if you scroll down, there should be this encyclopedia or book icon right here. And so you click on that. Alternatively, you can go there right away by typing in this URL. So aflow.org, Crystal database, and it is case sensitive. So hopefully that answers that question. No problem. Are there any other questions about the online portal for viewing the prototype structures? Okay, so if there aren't any questions, I'll move on to the next part, but feel free again to stop me and ask any questions via the chat. Okay, so let's go back to the slides. Okay. So now we're on slide 8. And so now I'm going to go more into how you actually generate these prototypes via the command line. And so there are there's the 600 that I showed that were online. And so these are part of the AFLOW Prototype Encyclopedia. And so they have a particular label designation. Oh, sorry, I'm jumping ahead. So they have this particular prototype designation that I outlined earlier. And then for these, you have to specify the degrees of freedom, the symmetry degrees of freedom for this structure. So these parameters. So you have to add this params flag. There are also some other prototypes that were actually started many, many years ago before I joined the group. And these are hard-coded prototypes. And so here you don't actually have to provide any degrees of freedom. And so, for example, I think we use this prototype label to generate the Heusler structure. And so this is hard-coded and it's generally numbered. So T stands for ternary, and then some number. So this was the first in our ternary scheme. And so you can generate either ones, but you need to be careful on whether or not you need parameters. And just as a reminder, if it has this underscore type label, then in general, you'll need parameters. Okay, so here's an example. So let's say we wanted to create the rock salt prototype structure. So it has this particular label, AB CF8 225 AB, and let's say we wanted to decorate it with magnesium and oxygen. So to do this, we use the following AFLOW prototype command, and it would generate this structure. And so one thing I want to point out is that in order to decorate it with magnesium and oxygen, we need to append to the label via colons the elements that we want to decorate. And so it needs to be in alphabetical order. And so in this case, magnesium first and then oxygen. And then there's only one degree of freedom. This is the A lattice parameter. And so we're specifying 3.5. So let's go ahead and actually create this structure via the portal. So again, if you're not logged in, please go into the portal, the on-demand, and then go ahead and if you already have a session, make sure you join that session because you can only have one session at a time. And then go ahead and launch the video desktop and you should get to this page. So someone asked, what do the degrees of freedom represent? So that's a good question. So I guess while people are loading the portal, I can answer that. So if you go, if I go back here, so the degrees of freedom are essentially what variables you can change while keeping this label the same. So if we change these degrees of freedom, we'll create a new geometry. And if we were to analyze the symmetries of this structure, it would preserve this label. And so I guess that's what I mean by the degrees of freedom. So it's the internal degrees of freedom for the structure consistent with the symmetry. So hopefully that answers your question. we're going to do a few exercises, so we'll actually see that how we can actually change these degrees of freedom, and maybe you'll get a better idea of what they're actually doing to the underlying structure. We're actually changing the structure, but it has the same symmetry designated by this label. Okay. All right, so actually I'm going to use the PDF version of the slide so it's easier to see now. Okay. All right, so hopefully everyone can see for the most part. May have to play with the screen a little bit, but okay. So if you're on the portal, I'm going to be using the terminal, and I'll try to go a little slower for those who aren't familiar, and I'll try to say everything that I'm doing. But first off, I'm going to zoom in a little bit. Okay, so hopefully everyone can see the text. Okay, so first things first is you need to make sure that you load the AFLOW module. So module load AFLOW, and you should see all of that pop up. And so if we do ls, we should see that if you're in the desktop, you should see that we need to go to AFLOW day 2. So we'll cd into that directory. And so now we're going to go into the 04 prototype XtalFinder directory. So cd 04, and if you hit tab, you should be able to autocomplete it. And so right now we're doing the prototype section. So we'll go cd1 protos. Okay, so first we're going to go into this magnesium oxide directory. So cd1 mgo. Hit enter, ls to see what's in there. And there's a readme just as a helper to see what we're going to be doing. Okay, so we want to generate this structure. So the AFLOW command is AFLOW -- proto equals, and then we put the label. So in this case, it's AB_CF8 225 AB. Oh, sorry, I'm looking at the wrong side. I jumped ahead. :MG:0, and then we need to specify degrees of freedom. So params equals 3.5. So this is the command, and if you hit enter, you should see that we've generated a postcard, and it should look exactly like this. And you'll notice that we wanted, so someone asked, why did you only use 1 degree of freedom? Good question. So the number of degrees of freedom is dependent on what prototype you're looking at. So in this case, this is rock salt, and there's only one variable that you can change based on this symmetry, and that's the lattice parameter A. Everything else is fixed. So this magnesium structure is fixed at the origin. So actually, that's a good question. So I'm going to go to the aflow.org crystal database. And let's go to rock salt. And so if we look at the equations, so we'll scroll down. So you'll see that, okay, so for the primitive vectors, there's only one variable we have to specify, that's A. So the lattice parameter A. And then if we look at the basis vectors, there are no variables. So there's no variable X, Y, or Z. They're all fixed. So it's 0, 0, 0, and half, half, half. So there's only one parameter you can specify. So it really depends on the symmetry of your structure, and that dictates how many degrees of freedom you have. So hopefully that answers the question in the chat. Okay, so I guess going back to the terminal, so we'll notice that we've decorated it with magnesium and oxygen. So let's say, I think we got a question last time, what does it mean to actually decorate? So if we hit up on the command line, and then if we remove magnesium and oxygen, what happens? If we just generate this structure, we'll see that we created the structure, but there's no physical elements on this structure. And so this is just a generic prototype structure with no decoration. And so in order to actually run a simulation, there needs to be physical atoms there. And so that's what we mean by decorating a prototype. We're decorating it with elemental species. So MgO, and we're back. You could also do sodium chloride, again in alphabetical order. And there you go. And so as I showed online, there's also many different geometry file formats you can use. And so in order to convert to those, you can simply, so I'll go back to the magnesium oxide command. You can easily convert to these formats by just appending them to the command. So if you do ---- VASP, it's going to be the postcar again. If you do ---- you'll get a CIF file. It's a little large because it has many Wyckoff positions in the general position. So, but if you're familiar with CIF files, it should look the same. So somebody asked a question, do you always have to separate the elements with colons? I think yesterday for one of the exercises, you separated some of the elements with commas too. Very good question. So for generating the geometry file like we are now, yes, they have to be separated by colons. Yesterday, we were creating aflow.ins, and if you'll remember, we were creating separate directories. And so since we were doing separate directories, we could perform many decorations at once. But with the prototype command, since we're outputting one structure to the screen, it would get confusing if you tried to basically use commas to specify different combinations. So for the prototype command in this format, there are no commas. Because then all of the postcards would just be printed to screen one after the other, and it might look a little bit like a mess. So it's a very good question. So there is a distinction between the Proto command and the AFLOW Proto. And yes, Corey mentioned that, yeah, they're different delimiters and they do different things, so. Okay, so we left off with CIF. We can also do aims, so FHI aims. And if you're familiar with that format, there's Quantum Espresso with QE. There's Abinit. And then finally, it's cut off here, but there's also ELK. So if you're familiar with that, this is something that we recently added. Okay, so there are any questions? Yes, so we'll see in slide 12, as Corey said, some more examples of the different delimiters. Okay, so now I've stressed, if you might have noticed that I stressed that the species have to be in alphabetical order. But what if you actually wanted to decorate magnesium or oxygen on the other site? And so to do this, we use this permutation feature. And so let's do this now. So if we do AFLOW ---- Proto equals AB CF8 225 A B, and so we're going to put dot and then BA. And so this specifies that we actually want to swap the A and B site with the different element species. And then again, MG and O, so they're in alphabetic order still. And then the params is still 3.5. We hit enter. So if we look compared to before, so I'll show it in the PDF, you should see that the magnesium is on the origin, but in this case, when we do this swap, oxygen is on the origin. And so in this case, it didn't really make much of a difference because these sites are actually symmetrically equivalent. So it's actually the same underlying structure. But in general, this may not be the case. It just so happens we have a highly symmetric structure. So somebody asked, what if you add more than two out? Oh.
Sorry, I was wondering if you could do a ternary as an example. I had a question similar to yesterday. I'll give you the designation for the cubic perovskite, and I was wondering if you could play with the ABC parameters to drive home the difference between ABC and the fact that things have to be alphabetically ordered. Here's the label.
Okay. So if we do AFLOW ---- Proto equals AB3C CP5, 221, A, C.
21, sorry, not 225.
Oh, sorry, thank you.
Yeah.
Okay, so let's just make sure, okay, we've decorated the structure. So in general, so this is a ternary. And so if we're using this permutation, basically designation, the default is ABC. And so I don't know what we want to decorate it with. We'll just do MN.
Well, so for example, perovskites, there's a lot of oxide perovskites. So if you can make some combination of A, O, and C.
Okay.
So do arsenic, oxygen, and then zinc, just for an example, just so you can see that the site is oxygen.
Is the
okay.
B site.
Yeah. So now, so for instance, the question was, what if you wanted to put something? Okay, well, we have to contrive an example, but if you do like calcium in the first site, and then you wanted to have arsenic in the second site, how do you make that distinction? And this is really driving home what decorating means, I think.
Okay. So we'll see that now the oxygen.
It has to be in alphabetic order, remember.
Yes.
The effluents.
Okay, so but we wanted oxygen on the B site, correct?
Exactly.
So in this case, we need to have some sort of variant where B is last and then AC, for instance. And so now we see that the oxygen has 3 sites and calcium and arsenic have 1 site. So yes, a great example, Corey, yes. And so this is the power of this controlling the atom site decoration. And so somebody asked, can we put 2 elements in 1 site? Excellent question. And if you're wondering if it's partially occupied, like or for a disordered structure, for instance, or it has partial occupation, you'll see that more actually in Corey's session. And so in one particular structure, right now we're considering ordered structures. And so basically they're fully occupied. So there's no partial occupation on these sites, but Corey's going to be.
No. Oh, sorry. I think what he's asking is, since you have 3 O's, is there a way I could put something that's not O and then the rest that are O? I think that's a different prototype, isn't it? Because those are symmetrically equivalent.
I'm sorry. So maybe I don't understand the question.
So you have right now in the example, I think what he's asking is you have an example where you have 3 O's, and I think what he's asking is, can I make one of those O's something else and keep the others O?
I see. Okay, good question. So yes, Corey is right that would be a different prototype in general, because let's say in this oxygen, let's say you wanted this particular site to be a different element. If you do that, now it's a quaternary. And if you look at the symbol, basically this first field, it says it's a ternary. So basically we're breaking this. And so it's actually a different prototype. And so you would need to put AB, 2, C, D or something. And so it would be a different prototype, and it may lower the symmetry and have different Wyckoff positions. So in general, yes, you can't decorate one site with 2 elements, at least in this way. You would need to go to a different prototype. But then, yes, there's the other, the flip side is if you're thinking partial occupation, which we'll see later. But hopefully that answers that question. But then someone had another question. So Mike, very good question. So on this example, you didn't use any parameters. How are the cell parameters defined now? So very good question. You're thinking ahead. That's actually coming up in the next few slides. So I'll hold off on answering that. But if I don't answer it, please message in the chat again. But yeah, a very good question so far. I appreciate people interacting. Does everything make sense so far? The distinction that Corey brought up? Okay, thank you. Okay, so yes, that's the atom site decoration. And so actually the question that Mike was asking is going to be answered in the next slide or so. So now, in this case, so let's go back to the rock salt structure. And so let's say we didn't want to specify the parameter, but we wanted to use what's known as automatic volume scaling. So if you're familiar with Vegard's law, basically we're using this scaling where we're looking at the volume of the particular element that we're decorating with, and we're using that as an initial guess for the volume. So we're looking at the volume of the magnesium and oxygen, and we're counting how many instances are in the structure, and then we're using that to estimate the volume. And so I'm fairly certain this is used in many ways of guessing the initial structure. So let's do that now. So, sorry, I'm kind of overlapping the slides a little bit. There we go. Okay, so to do this, we do AFLOW minus minus proto equals AB CF8 225 A B, and then we want to specify the normal decoration, so the default decoration AB, alphabetic magnesium and oxygen, and then params equals -1. So again, we saw that rock salt only has one parameter, and we want to signify that we want to use this automatic volume scaling. And so if we do this, we see that the lattice parameters are 0.5.5, etc. But you'll notice that we've changed the volume. And so this is where the Vegard's law comes into play. So for example, if we did sodium chloride instead, you would see that this volume changed because we're using different elements. So again, this is a nice initial guess for what we think the volume will be for this particular structure. And so next we'll go on to, so let me make sure that I answered Mike's question, or see that I'm going to. So in this case, so there was only one parameter, but now we may have others that have many, many more degrees of freedom. And so let's look at this particular example. So I don't know if you have the capability to copy this. I think you can use the clipboard functionality. But I'm gonna copy it. And then I think this is how you use the clipboard.
If the presentation is inside the portal, it's not. Okay, but if they open it inside the portal, then it'll copy and paste just fine.
Oh, okay, excellent. So yes, if you're using that, then I would recommend copying it from there, because it is a long command. So we'll go ahead and see if this, so we'll go ahead. Okay, so I at least have this. So
Can you open it up inside the portal and run it as if you were doing it from inside? I think that's easier.
Okay. Okay, so yeah, just give me a second to open it. Let me hide this. Okay. All right, so let me find the page we were at. A little too far. Okay. Oh. It may not let me. Oh, here we go. All right, so let's see, can I copy the whole thing? Copy. And the moment of truth. Nope. Oh, not quite. Oh, I didn't like the space, the new line. Okay, so I'm just going to type it from this point on. So it is AFLOW minus minus proto equals A B2 C OP 16 62 C 2C C dot ABC dot CU S SB. Okay, so you can see that that was, even just trying to copy and paste the parameters themselves was a little bit of a headache. And so especially if you have to specify many degrees of freedom and you want the default structure that we have in our database, it would be nice if we could just generate it a lot easier. And so we've come up with a solution, and we basically added this enumerated parameter set. So let's type that in here. And so if we do AFLOW minus minus proto equals AB2C 16 C to C, C, and then minus or dash 001. So that specifies in the enumerated parameter set, we're grabbing the first instance. And then dot ABC, CU, SSB. If I think I had a typo. All right, I think what I'm going to do is just use this original command. I must have a typo somewhere that I can't see. There we go. So if you look back to what we generated before, they should look exactly the same, minus this error message that's in between. And so this is a nice way to easily generate the command without having to specify these parameters for this particular structure. And so you may be wondering, okay, so I have this label and you don't know what parameter sets are available because there could be multiple. So if you just type in the prototype command, so let's do this particular prototype label. So AFLOW -- proto equals AB. So somebody asked a question, what if I want the postcard for a 3x3x3 structure? So that's a good question. We actually haven't covered it in this in these sessions today. I'm going to do this command really quick, and then I can show you an example of some of the functionality that we have. It's not in the lecture notes, but I'll do it on the command line in just a second. But good question. So AB2, OP6, 58, AG. And so we don't know what the parameters are. And so unfortunately, it's a little difficult to see since I've zoomed in so much. But AFLOW will give you an error message. I'm going to run this again to see if it formats better. Okay, it's a little better, but you can see that we have 3 parameter sets. And so if you do -001, then you use these parameters. -002, it's these parameters. -003, and it's these parameters. And so you'll notice that by default, it uses this -1 as the first parameter. So this specifies that instead of specifying the A lattice parameter, we're going to use the volume, Vegard's automatic volume scaling method. Okay, so now I'm going to go back to the question that somebody asked. So they wanted to know, what if you wanted to create a 3x3x3 supercell? So let's go to a particular structure. So I'm going to use the 001 parameter set. So first, let's just make sure that it generates a structure. There's no elements on it, that's okay. And then you can pipe it to a new AFLOW command, AFLOW -- supercell. And you wanted a 3x3x3. If I remember the command correctly, you should be able to do something like this. And you should see that it creates a 3x3x3 supercell. And so this is important for maybe slab or phonon calculations. And so I don't know if Marco is going to be talking about this in his session, but you can create supercells of structures with this command. And so I think you can specify it in this manner, or if you wanted maybe not a 3x3x3, but different variants, you could do 3x3x1. And I think you can also specify the 3x3 matrix if you'd like. So there's different ways that you can play with that. And if you want more information on that, I recommend doing AFLOW -- readme, if I can spell it, equals aconvasp. And you can search through that, and that shows all of the AFLOW commands, almost all of the AFLOW commands we have, and there should be the supercell listed in there. So hopefully that answers the one question. Someone else had another question. Is it the same algorithm behind the -001 as the params equals -1? Yes, exactly correct. So if you use the -001, by default, it's going to use the params equals -1 as the first parameter value. And so, yes, in this case, going back to this example, if you look in the title line, we actually tell you what label you generated. It was -001, and what the parameters are. And you'll notice when we use this 001 or this preset string added to the end, you see that we use -1. So yes, very good question. Okay, so hopefully that answers the two questions that I saw. So let's go ahead and continue back with the slides. Let me kind of rearrange here. Okay. And then so finally, I'm just going to recap what we talked about last time. So we were generating AFLOW-in files. And so if we want to do this, we instead of the -- proto, you might notice we did -- AFLOW_proto yesterday. And so if you put this AFLOW prefix, then it creates the AFLOW-in file. And so we did this yesterday, so I won't do it again for these commands. But then as a reminder, somebody asked about the comma versus the colons. So I'll reiterate that here. So only for the AFLOW-in generation, so this AFLOW Proto command, you can make many different AFLOW-ins at once. And so since you can do this, we can add the comma. And so if we do comma, this says generate this prototype and this prototype. And then for the species, for site A or species A, we'll say, we're going to decorate it with either silver, gold, copper, and iron on that site. And so you'll notice they're comma delimited. And so this is for site A. So then to move to the next site, we put a colon. And then this says that we want to decorate species B with manganese or titanium. And then colon for the last site, all of them are going to have zinc. So hopefully that is more clear for the person who asked about comma versus colon. And again, this is only for the AFLOW Proto command, not the -- proto command. And so last time we only showed the hard-coded version, but again, you can use the parameters to the AFLOW Proto command. So I will show this one. So if we do AFLOW, make sure I'm in the terminal. Okay, AFLOW --AFLOW_proto equals ABCF8 225 magnesium, oxygen, and then params, and we're going to be using the -1 variant. And so if you remember from last time, it's creating this set of subdirectories, and if you go in here, you should see the AFLOW-in with this particular structure. Sorry, it looks like I'm cutting the screen off a little bit. There we go. Okay, so :Q to quit. Okay, so are there any questions up to that point for generating prototype structures, either just the geometry file itself or the AFLOW-ins? If there are, feel free to mention it in the chat. And I think yesterday somebody asked, how can we see the full list of prototypes that are available? So one, you can look at the prototype encyclopedia, which has the 600. That's on aflow.org/crystal database. So you can navigate there with the different search functionality. So it looks like we have a question. Is there a way to visualize the structures after they're generated? So that's a good question. I think on this portal, I don't think we've tested any of the visualizations for visualizing on this portal, so I don't want to try it and have it break. I would say for now, I would use the aflow.org crystal database because there's a built-in JMOL viewer here. And so even if you're changing, we'll do calcite in this case. So even if you're changing the degrees of freedom, this is a nice way if you just want to visualize very quickly. If you want to change the parameter a little bit, maybe 0.4, and then refresh JMOL. And then you can see how the structure changed. So it's actually pretty small now. But yes, Corey also put in the comments that you can install JMOL on your computer. And so you can easily pipe these structures into any visualization software, whether it's Vesta, JMOL, and some of the others. So yeah, hopefully that answers your question. At least for today, I would use the interactive online. Otherwise, you can install visualization software and pipe the postcard there. And it looks like Corey's providing the link for JMOL. Okay, so one, you can look online to see, just double check. Okay, so alternatively, if you don't want to go online and if you want to see what prototypes we have in the command line, so I'm going to just go up one directory or two. So you can run the AFLOW --Proto. So you need an S. So this will give you the entire list of prototypes we have in this structure. So it's quite a big list. So I'm actually going to pipe this to a file, or redirect it to a file. Proto list. Hit enter. And I'm going to view what's inside. Use my favorite set no wrap, just so we can see better. And so there's some citation information at the top, and then at the top, we have these hard-coded labels. So here on the left is the label, then we have some symmetry information, so Pearson symbol, space group, and then if you scroll down, so these are all of the numbered, so hard-coded, so you don't specify any parameters. And then if you scroll down some more, we'll get past the hard-coded, and then we will see the ones that have, so these are the ANRL, so AFLOW NRL, and you'll see that they have the label that we're familiar with, and then also it specifies how many preset parameters we have. So in this case, there's a whole bunch of ones, but there are some that have 2 and 3. And so it tells you the space group, what their struct rubric is, etc. And so there's probably over 1,500 prototype labels that are hard-coded into AFLOW. So :Q to quit. And so let's say you wanted to search for maybe specific prototypes via the command line. You can also do this in the online portal, but let's say you wanted to get the labels that have, maybe, so they're binary, so 2 species, and they have a particular stoichiometry and are all space group 225. So you can do this with a command. So it's AFLOW --Prototype _ labels --n species, so for number of species, equals 2, --stoichiometry equals 1:2, --SG equals 225. And if you do this, it'll give you all of the labels that have these characteristics. So these are all binaries. They have a 1:2 ratio of the elements, and they're space group 225. And if you don't want to restrict the space group, you can also just remove the space group, and you should get a lot more. So that will, I think, wrap up at least the command line functionality. The last thing I'll mention is the README. So if you want to know more about the prototypes, or if you need a recap on the functionality, you can access the README. So AFLOW --README equals ANRL, and then let's pipe it or redirect it. And if we take a look, we see some citation information and then basically an overview of everything that I've just gone over. So feel free to look at it, and so you can kind of learn more about this functionality. So I realized we actually only stayed in this one directory, and I actually set it up into different directories, but basically they were outlining the different exercises, so you can feel free to go in on your own time. They have the READMEs, so they tell you exactly what to do for these particular commands. And there is a very, very small Python module, in case anyone was wondering. It's very simple. So, but if you go into the Python module directory, similar to the AFLOW sim functionality, so basically there's a class called Prototype. You need to make sure that you have AFLOW installed on your machine. And then there's just one command, so git prototype, and basically it's the same mechanism as before. So we'll do an example. So if we go into the example.py, we'll see that, so you need to instantiate the class, and then with a label, it's the same way that we've been doing it. So it's just a string, and then we're basically going to pass it to this functionality. So really, this is just to help if you're working with Python and you want to integrate it into your workflow without having to explicitly jump back out to the command line. So if we do :q and then Python example, and you'll see that it actually created the structures. And so in this case, it converted them to a JSON format, the structures. And so it's a JSON version of the structure. So it's not in a particular format like postcar or CIF. So just keep that in mind. Okay, and so I think those are all of the exercises here. So I guess up to this point, are there any questions before we break out into the breakout sessions? Okay, so if that's the case, before we break out, I'll briefly highlight the exercises. So in this first exercise, and actually they're all in this exercises folder on the portal. So we'll navigate there. So CD5. And then there's also the README, which just reiterates the directions. And so there's some hints there as well. Okay, so in this first exercise, we're going to use the prototype command to generate the following structures. So in this case, you're going to need to practice using the website. So you'll need to search for the diamond structure, Caswell Silverite, all of these structures. In your breakout group, you can feel free to divvy it up if you'd like to kind of cover more ground. But I recommend, if you go to the site, let's go back to the main page. I recommend just using the search banner. So if you type in Caswell, it won't do the whole thing, but you should see it come up. So that's an easy way to find the structures. And then what are the AFLOW labels, and generate them. And then the next one is you're going to take a particular prototype label. So this AHR1166A, and you're going to take whatever value of A you would like. So you can use the -1 or any value of A. And then you're going to create separate structures changing the C over A value. So you'll do, the first one will be your A parameter, then comma 0.5, and you'll save that structure. And then you'll do it for the others. So A and then 0.612. So you'll have 1, 2, 3, 4, 5, 6, 7 structures. And then you're going to evaluate the space group of these structures. And I want you to see actually how the symmetry may change. And then finally, we're going to decorate one more structure, the Heusler here, no parameters needed. And then you're going to analyze the symmetry with some of the symmetry commands we showed. And then what, if you had to guess, would be the AFLOW ANRL label, since you know how it's constructed. So for this first exercise, basically you just go to the website and you can type in all of these different variants, diamond, and then if you go to the particular structure, I clicked on the wrong one, but if you go to the bottom of the page, you should find the label and also the parameters. Sorry, JMO takes a second, but yes, here's the label, and in this case, there's only one parameter. So that's the procedure for 1. For 2, we use the command line, and all we did was did something like AFLOW --proto equals, then the label, HR1166A, and then params equals the first one, whatever we want, and then the second one we were changing, so 0.5. And then we were changing the second one to 612. And we saved all of these as postcards, and then we analyzed the symmetry with this command. And so you'll see that depending on what the parameters are, you can actually change the symmetry. So this kind of goes against what I was saying earlier, where if you change the parameters, it keeps the same symmetry. In general, though, you can sometimes fall into a higher symmetry category than what the label suggests. So you're changing the parameters and maybe you fall into, in this case, body-centered cubic. So the general rule is you either are in the same symmetry category or higher. And then the last one was we wanted to decorate the structure, this Heusler structure, and determine the space group and Wyckoff positions and Pearson symbol. And once you do this, since you know how to build the AFLOW NRL label, what would it be? And so in general, you should have been able to take the information and figure out what the label is. But we're going to show next time actually how AFLOW can do this automatically for you. And now I want to highlight a new method that we've been developing to actually identify and also classify structures as prototypes. And so we're going to be doing this with the AFLOW-XtalFinder module. And so what is the motivation behind this particular module? So we're working with large databases, large crystallographic databases, and we want to be able to mitigate duplicates. And so why do we want to do this? One is for data mining purposes, so we don't want to have skewed statistics by having multiple entries. I can't remember if this happened in my breakout session or if it was a question addressed to everyone, but someone was asking why are there so many silicon carbides, for instance, in databases. And the reason is that a lot of these have the same symmetry, and they come from different sources such as the ICSD or maybe a prototype library. And so we want to be able to determine whether or not two structures are equivalent or not. And so this is also important for machine learning since we don't want to have biased trained models. And in addition to this, so we want to be able to identify prototypes. So again, we want to find these backbone structures so that we can decorate with different elements to facilitate materials discovery. And so why is this difficult? It's difficult because if you remember from session 1, where Corey mentioned that we're modeling a macroscopic crystal via a small non-repeated unit, typically. However, there's many different ways we can, that we can represent this structure. And so here's an example of a crystal structure that's could be rotated or have an origin shift, or it could be in a different representation entirely. And so it becomes very difficult because there's different standard representations. And so how can we compare against all of these different representations? And so this is the motivation behind this particular module, which we call AFLOW-XtalFinder or Crystal Finder. And so the first main problem that we need to overcome is we need to be able to classify these structures. And so we need to automatically determine the standard label and internal degrees of freedom like we saw for the prototypes. And so there's functionality in this module to convert any crystal structure into its corresponding label and degrees of freedom. And so this is a very powerful tool because one, it gives us a mapping from the structure to this label, and it's consistent with the International Tables for Crystallography, which is the de facto standard for the crystallographic community when it comes to symmetries and Wyckoff positions. This is also powerful because it's tunable. So again, as we saw in the previous part, we can change these degrees of freedom and modify the cell accordingly. So we can either squish it by changing the C/A ratio, or maybe we can change the distances between these atoms. So again, by casting into this representation, we're able to manipulate the structure in this way. And then of course, AFLOW understands this label and degrees of freedom, so you can easily regenerate this with AFLOW. And so this is what we call the ideal prototype. So what the prototype would be for this structure. And so going back to the idea of being able to compare structures, we can do this on various levels. And so the first is we perform a symmetry comparison. So for example, we have these two structures. So here is a magnesium and oxygen structure, and then a sodium and chloride structure. They're in different representations, but we can compare their symmetry elements. So we can calculate their symmetries with the symmetry module that we have, which is again, very robust. And we can determine the symmetry operations in both structures. And then we can determine from this what the space groups are, and then also what the Wyckoff positions are. And then we can compare based on symmetry whether or not these structures are similar. And so we can compare first their space groups, and if they're equivalent or enantiomorphs, which means mirror images. So I didn't get to talk about this in the symmetry section, but there are certain space groups that are related via mirror images. They're mirror images of one another. And so these should be considered compatible. And then also we check the Wyckoff positions to see if they have the same multiplicity or similar site symmetries. So in this case, the site symmetries are exactly the same, they're mappable. However, for lower symmetry structures, these actually may be rearranged. So maybe it would be MM3 bar, for example. This is just a fictitious example. But we would need to permute this Wyckoff label to see if we can match it to this other one. And so this is what I mean by matchable. And so this typically occurs for lower symmetry structures. And so if we compare against this, then we're able to group structures as being isopointal, meaning having the same symmetry. And so this is an analysis that we perform. In addition, we can go one step further beyond symmetry, and we can look at the local geometry of the particular structure. So for example, we have the quaternary Heusler here, and we're going to be looking at what we call the local least frequently occurring atom geometry. So for example, if we look at this purple atom, and then if we expand out the cell, here it's a 2D projection in the center, and we want to determine what essentially the cardinality or the distances are between its neighbors. And so here we're only looking at the least frequently occurring atom. So in this case, there's 4 species and each of them are only 1. So we're looking at all of the distances in this case. But you can see that we're forming essentially these coordination shells of the surrounding geometry. And so we do analysis, so compare the angles and distances, and then we can use this as a metric to compare to other structures. And so we're looking at coordination, distance, angle, and relative positions. And so we can use this as a metric to compare to another crystal structure and start to glimpse what we call isoconfigurational, so meaning having the same structure. And so we call these isoconfigurational snapshots, since maybe the environments aren't exactly mappable, but they have similar local geometries. And so this is another analysis that we perform with this tool. And then finally, we can perform a robust geometric structure comparison. So here we're actually mapping atoms in the crystals to another crystal that could be similar. So for example, our favorite example is the rock salt structure. And let's say we have 2 representations and we want to know whether or not these 2 crystals are the same. So what we need to do is we perform a supercell expansion, and we want to try and find if there's a lattice or origin choice that can map to our original structure. And so we would do this, and we would find a potential commensurate match. And so in this case, it's the yellow lattice here. And then we need to be able to quantify how similar these structures actually are in this representation. And so here we borrowed inspiration from Bertzlav and Malinowski, who came up with this metric in 1997. And it's called the misfit quantity. And it's based on 3 aspects of the crystal. The first is the lattice deviation. So we're looking at how the lattice faces differ between the 2 structures. We look at the coordinate displacement. So we're trying to see if we were to overlay these 2 structures, what would be the distances between the atoms in one structure to the other. And that's captured via this metric. And finally, there needs to be a penalty if one, you can't map any of the atoms in one structure to the other, or if maybe they're too far apart. And so Bertzlav came up with certain ranges of the misfit quantity. And so if the misfit is less than 0.1, then the structures are considered to be matching. If the misfit is between 0.1 and 0.2, they're maybe within the same family. So maybe the structures are related via symmetry subgroups. And finally, if the misfit is greater than 0.2, the structures are said to not match. And so this is a metric that we adopted from Bertzlav and Malinowski, and we've done benchmarks, and we've confirmed that this is a reasonable estimation for the determining whether structures are similar or not. And so we continue this search until we've either found a match, or if we've exhausted all of the search space and we couldn't find a matching lattice or origin choice. And so this is what we call a geometric structure comparison. So this is mapping 2 structures onto one another. And so once we've done this, we've determined isoconfigurational structures. So they have the same configuration. And so with these analyses, so for the symmetry, the environment, local geometry, and the geometric comparisons, we can compare via these different comparison types. So we can compare by the same material. So here we have the yellow and purple atoms, and we try to map to reveal duplicates. So this is a material type comparison. We can perform a structure type comparison. So we ignore the element species and we're trying to find if the underlying backbone structures are the same. And this will help us to identify prototype structures. We can also do what we call decoration type comparisons. So given the structure, we can determine all of the different permutations of the atoms. So here we've swapped the black and gray atoms, and we want to determine if the decorations are equivalent or not. So we'll determine unique decorations. And then we can also analyze the magnetic moment. So if we have the spin, so if we have spin down on this center element and then spin up, are these, can these be mapped onto one another via these criteria? And so this will help us to identify distinct spin configurations. And so I'm going to go into a little more detail of the decoration type, since there's a little more involved here. And so as I said, it determines the unique permutations of an element for a given crystal structure. So again, another favorite example is the quaternary Heusler. And so there are 4 sites in the structure, and they're all equicompositional, so 1 to 1 to 1 to 1. And there, since there are 4 different sites, the number of permutations is 4 factorial, so there's 24 permutations. So there's 24 different ways that you can decorate elements onto this structure. However, if we use our decoration comparison technique, it turns out that only 3 of these are distinct. So some of these are duplicates with one another, depending on if you change the origin or are able to change the cell in some way, and they map onto one another. And so why is this important? So imagine if you're trying to create a database such as ours and you want to run all of the permutations for the structure. If you do this naively, oh, sorry, I jumped forward a little bit. If you were to just do this out of the box, then you would generate all 24 different decorations and run VASP calculations on them. And as we've seen, depending on the size of the cell, the VASP calculations can be expensive. But if we do this analysis beforehand, we see that only 3 are unique. And so we only need to represent these 3 because the rest are duplicates. So this is a great time saver, and it's very efficient compared to running all 24. Because if you were to run them, you would see that their results are degenerate. And so in addition to the magnetic type, so I already went over this, but the idea is that if you have 2 structures, it will determine whether or not, considering the magnetic moment, if these 2 structures can be mapped onto one another. And in this case, they're just related via an origin shift. And so we could easily see that these 2 structures map onto one another. So with these different comparison techniques, there are other packages in the community, and most only perform pairwise comparisons. So you would take 2 structures, compare them at a time, and you can only do 2 at a time, 2 at a time, 2 at a time. But again, we want to highlight this automatic framework that we've developed, AFLOW. And so in line with this idea or this methodology, we wanted to be able to compare multiple structures at a given time and have AFLOW take care of managing which ones are duplicates, what comparisons need to be performed, etc. And so given a set of compounds to compare, it does some grouping. So again, we do these symmetry comparisons, these LFA geometry comparisons, and also stoichiometry. And then they're partitioned into these groups, and then we compare the compounds within these groups, and some of them may not match. And so we need to go back and create new groups based on these criteria. And so we continue this loop until we've either compared everything and they match, or we've exhausted the comparisons to perform and everything is distinct. And again, to facilitate an automatic framework, we've also threaded a lot of these functionalities. So if you have many structures to compare, we've also multi-threaded or parallelized a lot of these analyses. And so you can spawn multiple threads if you have maybe thousands of structures to compare. And it'll do this on the symmetry, the local geometry, and the comparisons themselves. So it'll partition on these analyses. So in addition to these comparison techniques, so now that we have the mechanism to do so, we also wanted to go a step further and say, okay, we have all of these structures, but do they match to any established prototypes within the community? And so for instance, if we have an input structure, we want to know, does this prototype structure already exist in, for instance, our encyclopedia, our prototype encyclopedia? And so we have functionality to do this automatically. And so given an input structure, it'll search the library and it'll find candidate matches based on the symmetry comparisons and the geometry comparisons. And then it'll perform finally the robust geometric mapping, and it will determine all of the equivalent prototypes to this input structure. And so this is useful because, again, we want to facilitate materials discovery with this type of framework. And so if we have the functionality to determine whether or not a structure has already been studied, for instance, the prototype, then this can be, again, be a great time saver. And it can also help us to relate the prototype structures if maybe we don't know what this one is. And so we can get information on it, such as maybe its common name, structubric designation, etc. And again, going a step further is, what if you wanted to determine if your compound actually already exists in the entire AFLOW database? And so, for example, if you have a rock salt structure and you want to know what are the duplicate rock salt compounds in the database. And so this uses the underlying AFLOW search API, and Cormac's going to be talking about that in the next session when we talk about the organization of the database and querying the properties. And so with this functionality, the comparison or AFLOW-XtalFinder will use this underlying functionality to grab the potential matches to the structure, and then it will perform the relevant analyses, the symmetry comparison, the geometry comparison, and the robust mapping, and it will return all of the matches in the database. So for example, we have the sodium chloride, and here are all the matching compounds, and here are their unique identifiers, and then also how close they match to this, the input structure matches to these in our database. And we can use some of the AFLOW's API keywords, the keywords in our database, to query certain properties. So for example, if you want to find all of the matches and say, I want to know what the enthalpy per atom of these matching structures are, you can also query these via our API keywords, and you can see that all of these have similar enthalpies. And so again, this highlights the structure property relationship, which says that if structures are similar, then they should in general, or would in general, have similar properties. And so again, this is a nice tool that we've implemented as well. So I did mention that there are other comparison codes available to the community, but what I really want to highlight is that AFLOW-XtalFinder is not just a comparison code in itself. It does more than that. In particular, it's a prototyper. And so none of the other codes are able to cast a structure into this prototype designation, which is probably one of the most important features of this module. And there are other important features such as comparing to database and prototypes that a lot of them don't have. And then also not a lot of them are able to perform multiple comparisons. And actually, because of the multiple comparison hierarchies that we perform, such as symmetry and the geometry comparisons, we are actually, we scale better when it comes with respect to comparing multiple structures compared to other software packages. And so here's just a use case, an example of how we were able to use this software to find more prototypes. So we went to the AFLOW ICSD repository that we have, and we used the comparison techniques to group by duplicates and prototypes. And you can see that we were able to remove duplicates. So these are the unique materials for the original and after DFT relaxation, and then also the prototypes. And so we were able to find approximately 15,000 unique structure prototypes. And then we've also grouped by symmetry so we can see what the different symmetries are for this, for these prototypes. And then this is important because then we were able to identify the 5 most common prototype structures for, let's say, the unaries, binaries, all the way down to quaternaries. And we use, and so somebody just asked, is this paper published? It's currently, it's been submitted, and so it's not available yet, but as soon as it is, we will let you know either via the Slack channel, or if you are signed up for our forum, the AFLOW forum, you'll get a notification there. But as of now, it's been submitted. And so why is this important? So with this, we've been able to, 1, determine the compounds, so the number of unique compounds that exhibit a particular structure. We determined what the AFLOW label was. We determined what the unique permutations were with the permutation calculator. And then we were also able to match to any existing prototypes in the AFLOW.org or the AFLOW Crystal database. And so we were able to identify that some haven't been represented in the library yet, or in the encyclopedia yet. And so this is, again, shows that we can use this functionality to identify new prototype structures that we don't already have and that we can't, that aren't in the AFLOW framework yet. And so actually already these ones that are missing have already been added for part 3, and we're already working on part 3 of the library. And so with this tool, again, we can find unique prototype structures to add to the encyclopedia. And so here's just a few more use cases where we've been able to use this module. Corey's going to show a little bit later the thermodynamic stability. And so again, we have a structural analysis in there, and this is used. We've used it to identify biometallic systems, symmetry constrained DFT calculations, and also for disorder. You can also use it as a way to compare crystal structures, but Corey's also going to highlight another method of doing that as well. Okay, so I guess up to this point, are there any questions about the overview of what this functionality does? If there is, feel free to post in the chat. But if there aren't at this point in time, we're going to start doing the exercises. So there's command line functionality, and there's also a Python module as well. So again, you can integrate this into your own framework. Okay, so first I'm going to exit out of this, and then, so I'm going to use the PDF so we can see it a little better. Taking a little while to load, but, and then also if everyone can go ahead and open up the Vidi portal. And we're going to be going to the terminal. All right, let me scroll down a little bit. Okay, so let's go ahead and open a terminal. Again, just so everyone can see, I'm going to make my terminal a little bigger and zoom in twice. Okay, so again, make sure that you have the AFLOW module loaded. Module load AFLOW. Oh, there we go. So I think we added the days, Lisa added the days, so make sure that you put AFLOW Wednesday, or I think if you just put AFLOW, it may work also, yes. Okay, so once you've added the module, if you're in the desktop, well, if you're in the desktop, we're gonna go to AFLOW day 2. And we're going to go to the 04 directory, so 04 prototype XtalFinder. And now we're going to the second directory, so CD2 XtalFinder. Okay, so here are the exercises. So let's go to directory 1. We're going to do the first 7 of these together, and then we'll break up for the last into breakout sessions for the final directory. So, but we're going to go to CD1, map to prototype. Okay, So let's see what's in the README. Okay, so it corresponds to the slides here. So in order to calculate the standard label and internal degrees of freedom, we're going to use the following command, AFLOW -- prototype, and we're going to direct the input file into the command. So it's AFLOW -- prototype, and then we're going to direct in, we have 3 postcards in this directory. So we're going to do postcard 1 to start. And if we do this, you should see that, okay, we have the AFLOW label, the parameters, so these are the degrees of freedom that can be modified based on the symmetry, and then the actual values for this structure. So the last exercise in the prototype section, I was asking if people could build this by hand. So basically, what would this label be? So but here we're showing that with this module, you can automatically determine not only the label, but the degrees of freedom and their actual parameters. And so let's do this for all 3 structures. So if you hit up on the command line, you'll get the previous command. And let's do postcard 2. We see this one takes a little longer. I think it has more atoms in the unit cell. Yeah, it has almost 108 in the conventional cell. And so here we've been able to generate the label for this, and for 3, again, we have another one. And you can see that we have more degrees of freedom. So A, and then B over A, C over A, beta, and then the label as well. And so we also have a Python module for this. And so here I'm just going to show you the example script. So VI example, hit enter. I'm going to set no wrap. And so similar to the symmetry module, we have to import the module. So we're giving the path to where the module sits. We're importing the XtalFinder class from this Python file. And then we're instantiating the class. So again, you do need AFLOW installed on your machine to perform this. And then we're going to use the git prototype label and pass in the input file. All right, so :Q to quit Vim. And then let's run this. So Python example. And so you should see we get the exact same thing, but again, it's in a JSON object. And so again, this is easily integratable into a Python workflow. So you can convert it to a Python dictionary. And so that's what we show here on the slide as well. So any questions about the prototype functionality, what this does? If there is, again, feel free to post in the chat. Okay, so that's the first functionality. So let's go into the second directory. So we're going to go up 1 directory. So cd // ls, and we're going to go into directory 2. Okay, so in here, we'll cat the README. And so in this case, there's actually quite a few directions. So here we want to compare materials. So we want to compare structures that are comprised of the same structure and also have the same elements decorated on these particular sites. So these are what we call the material type comparisons. And so there's a few ways you can do this. You can compare a list of materials via this command here. So AFLOW -- compare materials equals, and then a comma separated list for each of the input files. And then in addition, let's say you have an entire directory of materials. So you can compare all of the materials in the directory with AFLOW -- compare materials -d for directory, and then the path to the directory. And then you can also perform for pairwise comparisons. So if you're just doing this list functionality and have 2 structures, you can add this print flag, and this will give you some more mapping information. So to do this, there's going to be a little bit of work that we have to do, but we'll do it together. So first, we're going to make a directory. So if you're familiar with the command line, make directory is mkdir for make directory. And so according to the instructions, we're going to make a subdirectory called structures. So structures, so make directory structures. If we do ls, you should see you made this, okay? And so now, according to the directions, we want to create the corundum-based structures. And we're going to generate 6 structures. And they're going to have slightly different parameters. So we're going to do this together. And so to do this, we're going to do the prototype command. So AFLOW -- proto equals. And so this A2, B3, H, R10, 167, C, E, and then the params are listed here. So each structure is going to have a different set of parameters. So it's going to be dash dash params equals, so 4.8, comma 2.7, comma 0.35, 0.56. And we're going to save this. So we're going to direct the output to structures. So in this subdirectory, and we're going to call this 1_base. So this is our base structure. So hopefully everyone can see that. And we're going to hit enter. And so we've saved that structure. And so what's going to be really useful now to generate the rest is to hit up to get the previous command. Now we're going to change the name of the postcard to 2prim. So we're going to generate the second structure, which is 2prim. And then we're going to add a pipe. So we're basically going to create the structure. And then we're going to use another AFLOW command, the sprim, to convert this structure to the primitive representation. And we're going to save the structure. All right, so hopefully everyone's following along. If not, I'll do this and you can at least see what the results would be. So now 3, we're going to make the conventional cell, 3 scond. And we're going to modify this line here. So it's going to be, instead of sprim, scond. So we made the third. Now we're going to change it. So this is 4. And we'll call this pos, since we're altering the atom positions as shown in 4. And so we're going to remove this pipe command. And now we're going to modify. You'll notice we've modified the last two positions. So instead of 3, 5, we're doing 3, 6, and 5, 5 instead of 5, 6. So 5, 5, and 3, 6. Oh, 3, 6. Hit enter. All right, so now hit up again. Now we're doing the 5th one. So this one, we're going to be altering the C/A ratio. So 5 C/A. We're going back to 5, 6, and 3, 5. 3, 5, and then 2.65. Hit enter. And then the last one is a combination of 4 and 5. So 6 C/A and pos. And so it looks like it went away, but I think I know what it should be. So it should be 5, 5, 3, 6, and 265. Okay, so we've generated all the structures, a little bit of work that we had to do there. But if we cd into this directory, we go to the structures, and we should see all 6 of the structures that we made. Okay, and so now we also know how they differ. So we changed some of the positions, we converted them to different representations. So now let's use the comparison feature to see how these structures differ. So to do this, make sure that you're back up in this directory. And you're going to do AFLOW -- compare materials -d for the directory. And then you're going to put structures. Okay, so if we do this, hit enter. Oh. I made a mistake. I should have put elements with these structures. So unfortunately, it might take more time to do this. So I'm going to do a little trick. I'm going to remove this. And then I have a little backup where I will do, there's a hidden directory, run exercises. And so I'm going to recreate these structures. So sorry, I should have decorated because the program was expecting that we had element species on here. And so there's a lot of output. And okay, that's fine. Okay, so I guess at this point, you'll just follow along for this example. Sorry, I should have decorated the structures. But so if we look in here, essentially it's the same structures. But if I look at them, I remembered to actually decorate them with the correct species. So that's my fault. Or yes, someone said you could use a sed command to fix. I wasn't sure if people were familiar with the sed command. But feel free to, if you want, you can revisit these in the exercises. But for now, I guess maybe I'll show it for everyone what the results are. So again, if we do AFLOW compare materials minus D, and in this case, I called it XtalFinder structures. Okay, so we're ignoring anything that's not a geometry file in there. And then it looks like, okay, so it did do it. It was just very fast and it's hard to see the output. But if we look inside these outputs, so we see that we did a material comparison and what's the output? So let's look. So if we do VI material comparison output dot out, set no wrap, then we can see that, okay, so it classifies the particular structure. It gives us some of the symmetry information, and it says that there were 4 duplicates. And it used this one as the base structure. So this is considered the, I guess, the master structure. And then the duplicates. So it matches. Let me open this a little bit more so we can see. There we go. So we can see that it matched to the 2nd, 3rd, 4th, and 5th structure. And so it makes sense that it matches to the 2nd and 3rd since these are just different representations. So we just converted to standard primitive and standard conventional. Then we also see that we modified the position in the C over A, and they're pretty close to what the structure should be, or they still match, but the misfit is slightly higher. And then when we changed both the positions and the C over A, it was too much and they didn't match anymore. And so this is in one command how we were able to compare all of these structures and organize or group by equivalent materials. And so :Q to quit. We also have a JSON output. And it does a similar thing, but it's in a JSON output. It's kind of hard to see here, but they're organized by, or they're grouped by equivalent structures. And so if we move out of this directory, there's also a Python module for this. So if you go into example, again, a similar framework, we need to specify the structures. In this case, I'm going to modify it since I renamed it XtalFinder structures. And then you can perform the same analysis with this compare materials directory and pass in the directory. So we'll do save :WQ. And I'll run the example again. I'm sorry if you aren't able to follow along since I made the mistake earlier. But you can use this Python functionality to perform the same analysis. Okay, so there are any questions there about using comparing materials, either Python or command line? And again, Okay, so someone asked, how do these functionalities work with special types of geometries, such as 2D materials with vacuum or surface slabs? That's an excellent question. As of now, the functionality is really only for 3D structures. So 2D structures, it's not, it doesn't handle 2D structures. And then also for vacuum, there's also the void. And so that hasn't been integrated into this functionality. We may be extending it in the future, but right now, for purposes, we're really interested in alloys that are periodic in 3 dimensions. And so we may extend it, but as of now, it's just 3D materials. So, but that is a good question. So I guess at this point, you would use just maybe the symmetry analysis, but again, with vacuum, that can mess up your symmetry. So it is a good question. What about deformed 3D materials? I guess if you mean by deformed, if you're changing the lattice parameters or modifying the positions, you can do that if I understand your question correctly. So yes, if the structure is deformed, but it's still a 3D periodic structure, it can perform the analysis, if I understand your question correctly. But yes, good questions. Okay, so we'll go ahead and go into the next directory. So let's see where we're at on time. Okay. So let's go into the third directory. So CD3, so compare structures. All right, so I'm gonna fix this. All right, so here's a summary of the output that we've seen. And if you want, I'm gonna skip this for now, but this is in the notes. So actually, if you perform 2 comparisons at a time, and you add this print flag, as I mentioned, okay, let me zoom in, then it will give you some comprehensive mapping information. So for example, if you loaded these 2 structures, it will give you some more output. What are the lattice parameters? It'll tell you the misfit, and then it'll actually tell you which atoms map to one another in the structures. And it'll give you the figure of deviation, so how much the lattices differ, the displacement, figure of failure, and then finally it'll give you the structures in their closest mapping representation. So that's with the --" print command. And that's only if you're comparing 2 at a time. Okay, so we compared materials, but now we want to identify the same structure type. So if you go to directory 3, and if we do cat the readme, so now we want to compare structures regardless of what elements they're decorated with. And so in this case, I've already given you a bunch of structures to compare. So if we do cd structures, we can take a look at what's inside. So we can see that we actually have many different structures. Looks like we have almost 40 structures. Let's go back out of the directory and let's perform a structure type comparison. So to do this, we're going to do AFLOW -- compare structures -d structures. And then let's say that we wanted to remove the duplicates beforehand. So we want to group into prototype structures, but we want to remove any duplicate materials beforehand. So we can add this remove duplicates flag. So let's do that. -- remove duplicates. And so there's 45 structures in here, so it'll take a little longer than it did before. It's ignoring anything that's not a geometry file, so that's what these warnings say. It's performing the symmetry analysis right now on all 45 structures, so this may take a second. Then it's going to perform the LFA geometry analysis, and then finally it'll do the mapping. So I think this may take maybe like 10 seconds or so. And again, you can speed this up with the by specifying multiple processors. We won't do it here just because we have a limited number of processors, but it's already done. So if we go in the directory, cd structures, and then if we look, these were actually already here when we looked, but here we see that we have 3 or 6 files, both 2 or 3 that are human readable.out and 3 that are JSON. So in the duplicate compounds, since we added this remove duplicates flag, if we look, we see that it did first the material type comparison. And so we see that there were some matches and the number of duplicates. And then if we do :q, and if we go to the structures, structure comparison dot out and set no wrap, we see that it also, you'll see that it also did a decoration comparison, which we'll see next. But you'll also see that here, even though they might have different elements, they're in the same category because we did the structure type comparison. And you might also see that if we scroll down here, for instance, you see that there are 9 duplicates, 9 material duplicates, duplicate compounds, and 1 structure type. So again, this is taking into account what duplicates were removed, but it's considering the count that actually there's 9 structures that map to this. Okay, so that's the structure type comparisons. We also have the Python module. I won't go through that in the interest of time, but it's exactly the same as we saw before. We just do compare structures directory. Okay, so :Q. Now we'll go to directory 4, which is the compare decorations. Okay, so now if we want to determine for a particular structure, what are the unique decorations? So you can do this with this command here. So according to the README, what do we need to do? So we're going to create the quaternary Heusler structure. So we're going to do this with the prototype command. AFLOW --proto equals ABCD underscore CF16 216 CDBA. And then I'll do ABCD, and then we're going to save this to a file. We'll call it quaternary Heusler.postcard. And so if we cat the postcard, we should see that we made the structure correctly. And then we're going to run this command. So AFLOW --, unique atom decorations. And then we're going to pass in the postcard, quaternary Heusler. This may take a few seconds, but here we go. So with the example I showed, we do see that there are actually 3 unique atom permutations. And so here we can see that all of these are equivalent to one another. And if we wanted to know what the misfit was for each of these, we can add the following flag. So print misfit. And it'll do it again, but it'll also tell us how close they match. So the formatting's messed up a little bit just because my screen is so large, but you can see that the 0 is actually, that you can see that they exactly match. And again, you can do this with the Python module. And so I'm just going to write it in this case, so Python example, and it will return it in a Python dictionary or a JSON object. All right, so for spin configuration, we'll go on to the next one. So CD5. So we're going to compare magnetic structures. So similar to what we did with the symmetry module, we're going to use the baseline command. So compare materials. Yes, Corey brought up a good point on the misfit value for the deformed structure question. So if we want to do the magmom flag, or if we want to compare magnetic structures, we use the magmom flag like before. And again, you can provide it explicitly. And so here you would specify the magnetic moment for the first structure, comma separated for each atom, then colon to separate structures. So this is for the second structure. And finally, colon for the third structure. And as promised, I mentioned that you could also do this. AFLOW can read the in-car or out-car, and it can process that information and grab the magnetic moment information from there. And so let's do that. So just to see what the README tells us to do, we're going to compare the chromium systems. So we're going to do AFLOW --, compare materials equals, And then we need to give the paths to the structures and then the incars. So actually, before we do this, I'm gonna go into one of the directories just so you can see what's in there. So this looks like we started an AFLOW run. We just generated the files. And so we wanna grab the postcar .xz, so this one, and then the incar.xz. So to do this, we're going to run the command aflow -- compare materials equals, and we need to go into the directory. So 1 cr up, down, postcar.xz, comma, so that's the path to the first postcar, then 2 cr down, up, postcar.xz, and specify the magnetic moment. So -- magmom equals, and then we're going to specify the path to the incar. So again, we're doing the same thing, up, down. It has to be in the same order for the geometry file. And so incar.xz, comma, 2 cr down, up, incar.xz. If we do this, again, it's kind of hard to see because my screen is so zoomed in, but we can see that they match. And if we scroll up a little bit, we should see that, it says you included the magnetic moment. And so we've detected the magnetic moment. And it compared the structures and they match. But let's say we create something just to see if it works if they don't match. So I'm going to do this quickly. So if we just do magmom equals, I'm going to specify it explicitly. So let's say we did a ferromagnetic case, and then we did an anti-ferromagnetic case. Oh, I mistyped. And now you see that they are unmatchable. And that's because we considered the magnetic moment and we couldn't match them because they had different spin configurations. And again, you can do the same with the Python module. I'm just going to run it in this case. And you can feel free to look at it later on. So we can see that this is the representative structure and the duplicate. And you can see that they match when we specify the magnetic moment. Okay, so we'll go to the next set, which is compared to AFLOW protos. So we'll go into this directory, directory 6. And let's see what we want to do here. So now we have a postcard and we want to compare it to the AFLOW Prototype Encyclopedia. And we do this with the compare to prototypes command. So again, just cat the readme for more information. So we have a mystery postcard. So let's cat postcard and pipe it to the command. So aflow -- compare to prototypes. And if we do this, so we're finding all of the matches that in the database, in the encyclopedia. And then maybe if I open this a little more, we can see. It's a little hard to see. Let me run it one more time just so we can see what they actually match to. There we go. A little easier to see. And so you can see that our input structure matches to the prototype designations 4, 5, 7. So these are the hard-coded, and then this is the ANRL type format, and you can see that it matches exactly. And so again, as per usual, we have the Python version. And so Python example, and we should see a similar thing. We'll run, and again, we see the same results, just it's been formatted a little differently. Okay, so somebody asked a question, what's the difference between this method and the prototype one? Excellent question. So the prototype method is it creates, let me scroll. Okay, so the prototype functionality is it takes any structure and it converts it into its exact prototype label and parameter value. While the other one will take the structure and compare it to the established prototypes that we have in the encyclopedia. And so it's trying to map to a standard. And so it's slightly different. One is the exact designation, that's the prototype, the minus prototype version. But then if you want to know if it already matches to something that exists, you use the compare to prototypes. So hopefully that makes sense. One is comparing, and the other is determining what is the exact label for that structure. Okay, excellent. So one person said, so there are a lot of duplicates between the hard-coded ones and the ANRL prototypes? Oh, so are there? There are some, because the hard-coded ones were started basically at the very beginning when AFLOW just got started. And so a lot of these were hard-coded, but then we've continued to develop this prototype generation scheme. And so recently, I'd say in the last 3 or 4 years, we've combined it with the ANRL prototype library, and we've extended it. And so there are some duplicates. And so you will need to be careful about that. But again, if you use this functionality, you can quickly identify the duplicates. But, and then there was another question, but what about inside the ANRL? There are not duplicates unless you play with the parameters. I'm not sure if I understand your question. I guess if you change the parameters in the ANRL structure, you may create a different geometry file. So for example, if you play with the parameters for one of these corundum structures, for instance, as we saw, if we change the parameters, some of them won't be duplicates anymore because we've changed the parameters too much. Okay, so yes. So that's why you can compare by symmetry and also the local geometry, but really you need to do all three to actually compare iso-configurationally. So you need to compare structures to structures after you've determined what the parameters are, because the label alone may have many structures that you can create, and they may be duplicates and they may not be. So that's why you need a module like this. So hopefully that answers your question, Mike. So it looks like we're running a little low on time, so I'm going to do the last one, and I think for the exercises, I'm just going to walk you through them. I don't know if we'll have time to break out into the breakout sessions. So if you can bear with me, maybe another 5 minutes, and then we'll go ahead and close the session out. But let's do these last two. So we'll do 7, which is compared to the database. So if you want to determine whether or not you have a particular structure and it exists in the aflow.org repository, you can perform aflow -- compared to database. So let's see how we do this. So let's take the rock salt structure that we have. So we are going to cat nacl, and we're going to pipe it to this command, aflow -- compare to database. And then, as I said, you can query certain API properties. So for example, the enthalpy per atom or natoms. And in this case, for the example, we're going to do 3. So we're going to do compare to database, then do -- properties to query certain properties. I'm going to move this over. And we're going to do enthalpy per atom, so enthalpy atom, comma, n atoms for the number of atoms. And then just to see, this isn't really a property of the material per se, but just the calculation time. How long it took to calculate this. Okay, and then we'll go ahead and run this. So this may take a few seconds because we're actually performing a AFLOW query, which Cormac will show later. And so it's grabbing all of the possible compounds in the aflow.org database that could match to this. And it's going to grab the candidates. Then we're going to perform the XtalFinder analysis. And then it will return the matching structures along with the properties. So again, it's loading the structures. It may take a second or two, so we'll wait. And then while this is going, there's also the Python module as well. And you can take a look later on to see how you would actually do that. So it's loading the structures. There was 32 that it had, out of all of the 3 million, it found 32 that match. And it's loading the structures. There we go, calculating the symmetry. And looks like it's taking a little longer than I anticipated. There we go. Okay, so it's done. See this file. So if we do ls, and if we do, let's open database material comparison output.out. And if we do set no wrap, we can see that based on our input geometry, here's some of the characteristics. And we found 27 matches in the database. And so here is the AFLOW URL. So Cormac's going to be talking about that designation. But then we can see the misfit value. So how close it matched to the input structure. The enthalpy per atom. So you can see they're all fairly close in enthalpy. And then the number of atoms. So some had 2, some had 4, depending on the representation. And then lastly, the calculation time, how long it took to calculate these structures. And so you can see, for example, there's 4 atoms in this case, and it took a lot longer than the others. So it looks like somebody had a question. Maybe they didn't finish it. It says, can ANRL maybe do something? Not sure if you still have the question or not. Feel free to post there. But, okay, so maybe another 2 minutes, and I'm just gonna briefly go over the exercise on how you would do this. So cd into the exercise directory. And let's see what we were supposed to do. Okay, so we're given a subdirectory of materials, and we want to perform the following analyses. So first, we were going to determine the unique materials via the material type comparison, remove any duplicates. Then of those unique materials, identify the prototypes, then calculate the distinct atom decorations for each of the prototype structures, calculate the standard label and internal degrees of freedom, and then finally, determine whether or not they exist in the encyclopedia already. And so if you were to do this, you might have performed a few different commands, but I'm going to show you that you can do all of these analyses in one command. And so, but before we do this, let's just look at what the structures look like. One thing that I wanted to highlight, if you look in the structures folder, you can see that actually we have 8 different structures, but they're in different formats. So we have the postcard, we also have the ELK format. And so what I wanted to highlight here is that AFLOW and AFLOW-XtalFinder can automatically determine what geometry file format it's in and load it into the module and compare accordingly. So again, using the ELK, AIMS, postcard, Quantum Espresso, you can compare any geometry file format that's supported by AFLOW. Okay, so what is the command? So if we do, I've hidden the answer here. So it's a hidden file. And so here's the answer, but here is the one command that we need to run. So I'm going to copy it. And then we're going to paste. So you can see that it's in one command. What we're doing is we're comparing the structures. We're specifying the directory, so structures. We're going to remove the duplicates, which was the first step. And then we're going to add the prototype designation. So that's equivalent to the proto command. And then we're going to add to the matching prototypes in the library. And so let's hit enter. So this may take a little bit because we're performing all of the analyses that are in that list. So it may take maybe 30 seconds or so, maybe less. So first it removed the duplicates, and then it determined the prototypes. And then, all right, it's already done. So let's go into the directory and let's see. So again, if we go into the duplicate compounds.out, again, we can see that these are all the unique materials specified here. So there are a few duplicates, I think. Yep, here's one duplicate. Then if we go into the structure output, then we can see that we actually have a lot more information. So we see that we also have the AFLOW label, the parameter list, the values. We have the matching prototypes that the structure matches to, and then also the unique atom decoration, and then what structures it matches to. So just with this one command, we're able to determine all of this information. So again, here's the different unique prototype information. And so this just, again, kind of going with the automatic framework or the automatic ideology of AFLOW, you can do a lot of these analyses automatically with one command. So I guess, are there any questions up to this point on the exercises or about the module itself? If there are, feel free to post in the chat. And let's see, so no questions? Okay, so I think that'll end it for this session. Oh, one last thing. If you'd like to know more about the prototypes themselves, I think I already mentioned this README ANRL. These are the prototype articles, so there's a lot of crystallographic information in these articles, so feel free to explore those. And then the README for AFLOW-XtalFinder, if you do AFLOW --readme = compare,